So a certified Microsoft partner. We're an Intel software provider. We're recognized by a handful of professional organizations for teaching their membership in the use of at-risk and decision tool suite for probabilistic analysis. And at-risk and decision tool suite is a primary Monte Carlo simulation tool at the majority of colleges and universities in North America and Europe, and that is rapidly expanding in Latin America and the Pacific Rim. So we estimate that today in North America alone, we have about 150,000 analysts actively using the software. And that's at every level of government, military discipline, all higher education levels, every type of business, industry, and business size imaginable. And that includes 93% of the Fortune 500 companies. So let's talk about one of the reasons why we're here, risk analysis modeling using Monte Carlo simulation. So the old way of risk modeling was to use single point estimates. So you'd have a financial model, some kind of spreadsheet, and you'd have single numbers in the cells. And hopefully you'd written your functions and calculations properly so the bottom line reflected the relationship between the inputs properly. The natural progression from single point estimates was to create three-point estimate or scenario analyses of the spreadsheets. So now you'd have, instead of 1 point estimate, you'd have 3. But the question often arises, well, what if things happen in between? What if these 10 things move in one direction at a certain time and those 12 other items move in a different direction? How does that cascade through a complex model? And how is one able to capture that kind of uncertainty and variation? That's how manual what-if analyses developed, and this is a very time-consuming, cumbersome, and error-laden procedure. So the new way of risk modeling is using probability distributions. That captures and the entirety of that uncertainty and variability to help make defensible business decisions for managing risk. And so those probability distributions, what they do is they furnish the decision maker with a full range of possible outcomes, not just a 1 point or a 3 point estimate, but also how likely those outcomes are to occur, and it also identifies the main drivers that impact the bottom line. So let's talk about Monte Carlo simulation quickly. It's a relatively simple concept. Essentially what you're doing is conducting a virtual experiment on your PC or laptop, and you're repeating that experiment hundreds, thousands, tens of thousands of the times, collecting that data. And that data is controlled by you in terms of setting the parameters of the inputs in terms of how much they vary and the relationships they have. Once you've collected the data, then you can organize it. And that in that organization, you're able to better analyze what's going on in complex systems to improve your decision-making process. So let's use a very simple example, rolling a pair of dice. So I'm going to ask you to imagine that you don't know how dice behave when you roll them. And so one of the first things we need to do is define the parameters of rolling dice. In this case, you have one of the parameters is you have 2 dice. And every time you roll them, you have 6 possible outcomes for each die. So what happens when we run a virtual experiment and roll those dice 48 times? Well, we get a bunch of numbers. And I'm going to rhetorically ask, does anyone see a pattern in those numbers? I certainly don't see the pattern. So to make things simple for me is I'm going to look, rather than all of the outcomes, I'm going to look at just the totals, sort of condense what's going on. And so here we have the totals. It's fewer numbers to look at, and now it's a little bit easier to decipher what's going on or what the pattern is. But again, for me personally, I don't see the pattern here. There's probably 1 in 1,000 people that can quickly say, oh, look, there's more 7s than anything else. So this is where the software comes in, is you can now organize the figures. And in organizing the figures, you're able to understand the behavior of rolling dice. And from here, we get the famous histogram. And so you can see that lucky number 7 is the most frequently occurring die that are rolled, with I've heard these are called boxcars. I heard that a couple of months ago. Double sixes are boxcars and snake eyes are the 2-2s. They're the outliers. But with 48 dies, 48 rolls of the die, this is not a smooth curve. It's kind of jaggedy. So I actually have an example model that smooths this out for us. Okay, so let's review. Monte Carlo simulation is a virtual experiment that repeats a process or project a large number of times, generating a large number of random samples bound by a specific set of parameters that the end user puts in. Those numbers are then collected, organized, and analyzed. So the benefits of using At-Risk. It's easy to use. Number one, you're working in a familiar environment, which is Microsoft Excel. So at-risk functions or true Excel functions means you can copy and paste, copy and drag, draw cell references across worksheets and workbooks, nest Excel functions with at-risk functions. It behaves exactly like you'd expect Excel to behave. Number two, peace of mind. We've been around for a long time. We're approaching nearly 30 years of being in business, and as we've put our software out there, we have a pretty good cross-section of our customers that are vocal about any bugs that they might find or questions they may have. And we take that input very seriously, and the result is that we have very stable, highly regarded software. And perhaps most importantly, it becomes much easier to make defensible business decisions. After the heavy lifting, the calculations of the Monte Carlo simulation is done, with the click of a mouse, you have access to dozens of charts and graphs and reports to help you inform the decision-making process. Okay, I'm going to briefly go over the tools within the decision tool suite. At-Risk is what we're going to be spending the bulk of our time with, as well as RISKOptimizer. The other tools that I'll be mentioning here, it's just a summary. Risk Accelerator is a built-in function that harnesses the multiple CPUs within your device to help make the simulation optimizations run quickly. Precision Tree is also an add-in to Microsoft Excel. It's a decision tree and influence diagram software. It integrates very nicely with At-Risk. Top Rank is a what-if or sensitivity analysis tool. Some people sometimes confuse it with what At-Risk does. At-Risk actually does top rank work, but it sometimes takes quite a bit longer to place all the parameters and distributions and correlations and that type of thing into a model to do a full analysis. What top rank does is it identifies very quickly what the top drivers are in any model. So if you have a customer or a stakeholder who gives you a model without any explanation, you can run a top rank analysis very quickly to get a sense of what the main drivers are in that model. Stat tools I like to call a nice little stats package. It's not like a Jump by SAS or a MATLAB or a Minitab. It focuses on 37 of the most popularly used statistical procedures, and unlike Microsoft Excel, it reduces the number of clicks you have to do to get to certain information. For example, if you're trying to figure out what the coefficient value is between two data sets, it's about half as many clicks to use stat tools, and it's more intuitive than Microsoft Excel is. Neural tools, also an add-in to Microsoft Excel. It's a neural network tool that trains a neural net based on your data set and then makes predictions of what may happen in the future. Evolver, I like to call the little brother or little sister of RISKOptimizer. These are both optimization tools. Evolver does the optimization with discrete numbers. RISKOptimizer does the optimization under uncertainty. And I'll have a demonstration so you can understand that more fully shortly. Okay. Beyond that, we have At-Risk for projects for scheduled risk analysis. We are not going to be focusing on scheduled risk analysis today. I'm planning on scheduling another separate WebEx to focus on scheduled risk analysis in potentially next month or the following month. We also have developer kits, books, professional training, consulting, custom development, all to help support the use of the tool. Okay, let's get into some modeling now. Oh, there's the pricing, but I'm going to get back to that in a little bit. One moment here. Okay, so at this point, you should see Excel. This is the ribbon menu that most of you are most familiar with. With that risk, it adds into Excel, and you get our own. We put a place in our own tab with our own set of menu items. So I'm going to open up a very simple model, which is a dice model. So one thing to think about, or to keep in mind, all of my models, the cells that are colored in yellow have at-risk inputs or distributions, while the pink ones are at-risk outputs. So in a dice model, we have, in this particular dice model, I have 2 die, and they're both normal, everyday kind of die. At least they're modeled that way. So this is a syntax that we use to define how a die behaves when you roll it. You don't have to worry about the syntax or typing it out because everything is menu-driven in at-risk. So to do a visual examination of that distribution, you simply click on Define Distributions. And this is a distribution, so you can do a visual inspection on rolling a die. You have 6 possible outcomes, all with the same likelihood of occurrence. The same is true with die number 2. And in cell C3, what we're doing is we're adding the 2 die together as we roll them, but we're also assigned an at-risk output. So I'm going to delete this one right here to show you how to start from scratch. Empty cell. We still go to Define Distributions, and when we do that, let me open up this further. We're right now in our most commonly used distributions, but we have 79 to choose from. We shouldn't be overwhelmed by this because the majority of our customers only use 2 or 3, perhaps 4 at the most. So the one I'm interested in is the uniform distribution. So when I choose that, I can now modify the default in a blank cell. This is the default by using this portion or the control portion of the window. So the first thing I'm going to do is I'm going to change the minimum from 0 to 1. Then I'm going to change the maximum from 10 to 6. And that produces our distribution for a normal die. I click OK, and now that distribution is added to the cell. For an at-risk output, it's actually even more simple. I'm going to delete the at-risk output function, and this is just a normal everyday summation. And to add an at-risk output, to capture the uncertainty during the simulation, we need to click on Add Output. When we do that, at-risk tells us what the title should be. We click OK, and we're done. Now we're ready to simulate. And to simulate, we click on Start Simulation. We're going to do 1,000 iterations or 1,000 virtual rolls of each die. So let's start that process. So here we go. You can see the numbers are changing in here, and the graph is taking shape. And actually, I should probably do it a little bit more. Hold on a second. Do 5,000. So I want to show you that nice, smooth curve. So here we go. This is much more smooth. I'm going to speed up the simulation process. And after 5,000 rolls of each die, this is the distribution again. A nice, smooth curve, snake eyes and boxcars as the outliers, and lucky number 7 in the middle. Life is not symmetrical, nor are our models. So let's throw a monkey wrench into this. We're going to add a 3rd die. And in that 3rd die, what I'm doing, with that 3rd die, what I'm doing is I'm collecting doing a summation of cell C3 and F3. So the summation here plus the additional 3rd die. But let's take a look at that 3rd die. Here's a syntax. I'm going to click on Define Definition to Define Distribution to get a visual inspection. And this is our die. So what I've done when I developed this this particular die is I created a virtual hunk of lead that I placed on the virtual 6 side of this virtual die, so that the 6 most often just hits the table while the 1 is up in the air. So when we simulate this one, the numbers are all changing during the simulation, and we can speed it up by clicking on this little button right here. So that'll stop these numbers from changing visually. They're still changing in the background, and the simulation speed up quite a bit. And so with 3 die, 2 symmetrical die and 1 that's kind of wacky, this is the distribution we get. 18 and 17 are very rare, 16 and 17 are pretty rare too, and here are the most frequently occurring numbers. We can actually pull this over and say that this is 8 through 11 are the most frequently occurring values. In fact, 8 through 11 occur 38% of the time. 3 through 7 occur 35.2% of the time, and 12 through 18 occur 26.7% of the time. So that's the basics, the most fundamental basic part of using at-risk. What I'm going to do now is move into a very interesting NPV portfolio model. It's more germane to business analysis. Okay. If you have a commercial license of at-risk, or you have a trial license of at-risk, you can actually find this particular model by going to the Help menu and then clicking on Example Spreadsheets. And doing that opens up an index to example spreadsheets. And you can find dozens of different kinds of models, both based on a specific business application or highlighting a specific feature in the software. So when you click on any one of these, it opens up the actual model. This is the index. And again, you can get there by going to the At-Risk Help menu and then Example Spreadsheets. So with each example model, the first tab is an explanation tab. It gives a summary of what the particular model is about and what we're trying to convey. In this particular model, what we have are 8 different projects, all with NPV information in it. So this is the one we're going to be spending the most time in, Project 1. But Project 2 is a slightly different model. Project 3 is a slightly different model again for NPV. So we have 8 different projects that we're working with. All of these projects are then fed into the Model tab here. And so what we're doing here, and I'm going to talk about this a little bit more later, is we're gauging the possible success of each of the projects. And then we're going to be choosing which projects to take on to maximize our investment, or to maximize the return on our investment, but yet stay within a certain budget. So right now, if we selected all of the projects, we're going to be generating $2.5 million in net present value, but the cost is far exceeds the budget that we have. So before we get to that optimization problem, what I'm going to do is I'm going to spend time in Project 1 and going over several different features of at-risk before we even begin to simulate. So this will take a little while before we get to the simulation phase, but bear with me. And this is a little bit of a work in progress here. So first, let's focus on this set of items here. Right now, our target NPV is $365,000 for this particular project, Project 1. This is the expected value of this project based on cash flow being driven by market conditions, sales activity, and production expenses. So we're within 1%. The estimated value is within 1% of our target NPV. And so the question is, do you have, as a decision maker, enough information to approve this project? And how confident are you in your decision? In a deterministic model, which is what your eyes see right now, this is a difficult choice to make. What are the chances that we'll go below $365,000 if some of these items change? And so this is why we're here. We're trying to capture that uncertainty and variability. So the first thing that we're going to do is we're going to do a visual inspection of a few items here. So product development in years 2014, 2015, and 2016 are indicated here. So we're using a risk normal distribution. And again, we can do a visual examination by clicking on Define Distributions. And here we see that $50,000 is our mean, and the standard deviation is defined by another data set. In this case, it's $5,000 or 5%. or 10%. We look at product development number 2 for 2015. It's a slightly different number and curve, and then we have something different yet for 2016 product development. And things that get a little bit more interesting when you get into capital expenses. We're using a triangular distribution here, and we're looking at a highly skewed triangular distribution. And in 2015, we're actually skewed in the other direction. And then 2016, it's skewed even more so. So that's just a way to do a visual examination of some of the different kinds of distributions. So the next thing I'm going to do is use cell references to define the parameters for these items here, which is the sales volume. So when we go in here, we see a particular formula, and this particular formula drives some information within our cash flow. But this is just a single number, so I want to add variability to it because I'm not really sure whether I'm going to hit 3,000 or if it's going to be below or above that. And I have a data tab here that I'm going to be doing cell references to for the sales volume. So to do that, I'm going to click inside this cell and then go to define distributions. And I'm going to choose a PERT distribution. And then I'm going to use this button right here. So this button allows you to do cell references quickly to define the parameters. You can, of course, pop in here and just type in a cell reference, but this is a quicker way of doing it. So you click here. It opens up this tiny little dialog window. I'm now going to click on the Data and Estimates tab. And I'm going to click here and do it this way. Like that. And then here, and actually I have to change this to this. Okay. So now we're taking F14, F15, and F16 in the Data tab to define the distribution. The static value is our benchmark. It doesn't affect the calculations of the distribution. So when I click here in the corner, we pop back to our model, and we get the distribution based on the cell references from the Data and Estimates tab to define the distribution for sales volume in 2016. I'm going to click OK. And then what I'm going to do is I'm going to grab and drag all the way across. And if you notice up here, there's a lot of syntax in here, but the cell references are kept intact. So by building a distribution for one cell, we can quickly populate all the other cells, just like you'd expect Excel to work. So the next thing that we're going to do is we want to study not only the net present value for the entire model, but we may also want to study the cascading effects of all these market conditions, sales activity, and production expenses for each single year. So what I can do is I can collect the net income for each of the years, or select, go up to Add Output. Remember, At-Risk automatically chooses a name based on the titles that are given, and I click OK. So now what we've done is we've added an at-risk output so we can study what happens in every single year of our net present value model. Okay. Next, number 5. So this particular model I've modified. It's available in our in your trial licenses under example models, but I defined it so you can see. I'm sorry, I didn't define it. I refined it so that there are certain steps I'm going to take. And if you'd like to get this particular model and kind of repeat what I did, just send me an email. I'll be happy to do that. So the next thing is we're going to correlate some items. So let's correlate product development for 2015, 16, and 17. I think that's right, 14 through 16. To do that, what you do first is you select the data cells. And then you click on the fourth menu item, which is define correlations. And in doing so, a matrix is developed with the product development numbers. So what I want to do is I want to assign a coefficient value to to define the correlation between product development in 2014 and 2016. And I'm going to assume that this is a positive correlation and it's a strong correlation. So if we have high product development costs in 2014, they're probably going to be high also in 2015. And all coefficient values for defining correlations are going to be between -1 and +1. So in this case, let's say 0.75. And then I also want to do a correlation between product development in 2015 and 2016, and maybe we can call this 0.8. So very strong positive correlations. You can do a further visual examination by clicking on this little tiny button right here, and it creates a scatter plot of the coefficient values that we've added. And you can click on any one of these and kind of play around with the scatter plot slider. A coefficient value of 0 creates essentially a perfect circle. A negative coefficient value has a different angle from a positive coefficient angle. Let's go back here. I think this was 8. Click OK. And if the matrix isn't self-consistent, you can have at-risk make it consistent for you, so we'll do that. So the next step now is to place the matrix in our model. So I'm going to click OK. I'm going to go over here, click OK, and that matrix is now added to our model. So when you share the model with stakeholders or decision makers or other analysts, they can see that in this particular model, we've correlated these items together. And when you click on the cell and take a look at the matrix, you can see that we've nested the risk correlation function in there too. So the same is true here and here. All right. So item number 6. I'm going to do that a little bit later. I'm going to actually skip to item number 7. So what I've done in cell F19, is I've added a risk sim table. So this allows you to do sort of a simple scenario analysis. So for example, in 2016, we may have a new president. And in 2017, that president may drive and a new Congress, of course, may drive the tax rate up or down or keep it the same. And so this is based on, let me see, the Data and Estimates tab. Cool, so we'll go there and look at F21 and H21, which is here, F, G, and H21. So most likely, or not most likely, but the high may be as much as 50%, the low may be a 42% tax rate, or we'll just keep it at the current 26% tax rate. So when I do a risk sim table, I actually need to do three separate simulations, each of 1,000 iterations. The first simulation will be based on a 46% tax rate. The second simulation will be based on the 50% tax rate, right here. And a third simulation will be based on a 42% tax rate. And so we can compare what the differences in tax rates may, or how they may affect the bottom line. Okay. And the next thing I want to show you is time series modeling. This is a very new and very powerful tool that we've added to at-risk. So here we have inflation rate. And right now, when I go back to the data tab, you'll see that we're just at 5% all the way across. So let's go back to the data tab. Here's our annual U.S. inflation rate. And what I've done for 2013 to 2023 is I just have hard numbers in here at 5% embedded. So what I'm going to do, rather than guess that we're going to be about 5%, I'm going to delete all these. And we're going to do a forecast based on historical data. So I can just click in any cell within my data set, then go to time series and click on fit. We get a dialog window that describes a few things to us. First, we see a graph of how inflation behaved during, since 1972. And then to achieve, to prepare the data for forecasting, one of the things we have to do is to do a data transformation to achieve stationarity. If you know what you're doing, you can choose how to go about that. You can choose a function or a detrend or a deseasonalization, or you can have at-risk do an auto-detect. So when I click on auto-detect, it chooses the detrending data transformation function. And now I'm ready for doing a forecast of how inflation may behave in the future. The next step is to click on Fit. And so this window shows us several things. One is, again, the historical behavior of inflation. And then here's the cone of possible outcomes for inflation. Here's the mean. You can see it defined here. And here's the band from 25% to 75%, and here's the band from 5% to 95%. And this represents one sample path that inflation may take. You can animate this by clicking on this little button here, and you can see that the inflation will animate. So these are one possible scenario, another, and yet another. Most of the time staying within the 5th to 95th percentile, every once in a while bouncing out because we make it into the 99th and 1st percentiles. Another thing to take note is that we have two fitting tests that you can choose from. And in the fitting, once the fitting test is chosen, then at-risk decides which time series modeling function is best for this particular set, and it ranks them in order here. So we have moving averages and conditional heteroscedastic conditional works and Brownian geometric motion. These are a lot of things that go over my head, but these are very sophisticated time series modeling functions. This one is ranked as the highest. The next step is to write these to the cells of your data set. So when I click on Write to Cells, the default is to choose 24 periods ahead, but I only need to go a few years ahead. So I'm going to click there and click OK. And so now we've added this very sophisticated function for time series modeling, and we're looking at one possible path that may go through here. When I engage the two dice up here, and then I can tap on the F9 key, we can see another possible path that may take, and another, and another. And we can also simulate. So let me change this to 1, and just very quickly change this to 500. And just so for 2013, we can simulate the probability distribution for inflation. And there you have it. So it looks like the mean in this case is just short of 3%. The mode is a little bit lower than that, and you can understand what the standard deviations are. These output graphs are really great. You can slide them around and maybe look at the 10th percentile as opposed to the 5th. And if you can't quite hit it, you can just type in 10, and it goes to the 10th percentile. You might want to hit 1, 0.9, and it moves it for you. Okay, so let's go back to the project. And now we've added a whole bunch of features. So I think we're about ready to simulate now. So let's keep our eye on the projected net present value. Remember, now that we've added everything, we have a different number here to work with, which is very interesting. But that single number does not spell the whole picture. We really need to look at the full range of possible outcomes, and that is defined by running a simulation. So let's go back to 1,000. So we're going to do 3 separate simulations. Remember, the first at 46% tax rate, the next at 50, and the next at 42. And we're going to do each one 1,000 times. Okay, so during the simulation, all the numbers are changing and the graph is taking shape. I'm going to pause this just a moment here and move it out of the way for you, and then just restart it. So in demo mode, where all these numbers are changing, this is actually robbing my system of a lot of resources, so it's going a little bit slow. I can speed that up by essentially just turning these numbers so that they just appear static, even though they're still simulating in the background. You can see the simulation speeds up quite a bit more. So now we're done with simulation 1 and beginning simulation 2 right here. So this is taking into account the variability involved in capital expenditures and product development, sales volume, inflation rates, and a few other items too. And we're almost done with simulation number 3. Okay, great. So if we look at this, we have we can do several things. So again, we can move around the parameters. So for example, we may want to go to 0 net present value, There's only roughly a 2% chance that we're going to be earning less than zero, like we're going to be losing money on this particular venture. But remember, our target value is $365,000. So let's change this to 0.365 and move that over. So this is what we're now faced with. There's a 46.4% chance that we're going to earn less than $365,000, which is our target NPV for project 1. On the other hand, there's a 48.6 plus 5% chance, so roughly a 54% chance that we're going to exceed that. In fact, we may make a lot of money. So for example, if we go up to $600,000, there's nearly a 35% chance of exceeding $600,000. So if you recall, initially this was within 1% of our target net present value. It was a coin flip, but now we have more information to inform our decision-making process on what to do next. One of the common questions that comes after this is to ask, well, what's causing us, to have these kinds of percentages and possibilities? What are the drivers here? This button right here is our tornado diagram, and it allows you to look at 5 different ways of which drivers, in different ways, which drivers are impacting the bottom line. I like to look at this one personally. This gives us a coefficient value, and it's clear that the number of competitors are having a negative impact on our bottom line. Here are a couple of items that are having a positive impact, but with a 0.11 coefficient value, it's almost negligible. So the question comes up, if we want to improve our odds of achieving our $365,000 amount. Whoops, I hit the wrong one. If we want to improve the odds, like lower this number but increase this number, what we want to focus on is the number of competitors entering the marketplace. Maybe we need to get into the marketplace sooner, grab more of a market share so that it becomes more difficult for our competitors to erode our ability to earn money. Let's go back to this item. So remember, we ran 3 separate simulations. So now we can also study not only simulation 1 for a 46% tax rate, but we can compare that with simulation number 2. So here's a 53.6% chance we're going to be earning more than $365,000. This is the one at 50% tax rate. It diminishes our ability to earn more than that. And in simulation number 3, we went down to 42% tax rate, which improves it yet again. And you can look at these all as one simulation. This is a little bit difficult to look at, but you have ways to sort of make these transparent. For example, click and graph options, and I believe it's curves, and let's see, you can change this to a line, like so. And it makes this red one, the very first one, transparent. You do that for the other ones, and it becomes a little bit easier to visually understand how these compare to one another. Of course, you can look at the numbers too. So if I pull this out a little bit further, and then you can expand these. And now you can compare the means, for example, and the mode, for example, the standard deviations. So with a low tax rate, there's a much larger standard deviation, though our ability to earn money has improved. So there's a lot of volatility, and another thing to consider when making your decisions. All right. One of the nice things about at-risk that I mentioned earlier is you can now grab this data. Any charts and any graphs that you look at that are generated, you right-click and copy. And I'm going to bring my Microsoft project over again, and then you can simply paste any chart or graph into a PowerPoint presentation, Microsoft Word document, into an email. It's just very, very easy to get the information and share it with other people. So let me move that back. Which leads me to another item. What if you have colleagues or stakeholders who don't have a copy of at-risk? They can't run the simulation. In fact, when they get this model, all this yellow cells and pink cells if they don't have an at-risk license, will have something similar to this syntax all over the place. It'll just be a mess. They won't be able to understand what's going on. At-risk has a great utility called a Swapout function. When I click on Swapout function, what happens is the at-risk functions are replaced with their static or expected values. So when I click OK, I'm not going to save the simulation results. All these numbers now are cell references or equations or numbers. So anyone can look at this. In fact, you can embed the simulation results as their charts and graphs in any one of in another tab, and those will be retained as well. So everything that you've done, all the work that you've done, can be shared with anybody else. The only limitation with somebody who doesn't have an at-risk license is they can't run the simulation themselves. Okay, let's say somebody makes a change and they say, you know, that Andrew guy, he really doesn't know anything about product development. This would really be $50,001. Oh, let me change that. That's 500,001. There we go. Then they send the model back to you, but fail to tell you the change that they've made. When you click on swap in functions, we're going to replace the expected values now with the at-risk functions. They're going to come back into play. And you get a log of the changes that were made. So that log allows you to choose how to proceed. You can either keep the recommended, which embeds the 5001, can't quite see it here, as the risk static function, which luckily, in this case, it doesn't affect the calculation as a risk static value, because the cell references are retained, which is important. But you can keep that as a benchmark if you choose, or you can go back to what you had before. Swap in at-risk functions, and everything returns to the way it was. A couple other quick things. I'm going to run one more simulation. This is just one simulation rather than three to expedite things along. I'm going to go back to the tornado diagram. There's one other sensitivity analysis that's really neat, which is the inputs ranked by effect on output mean. This obviously differs from the correlation coefficient one that I showed you. Same basic information, but presented in a different way. So what this does is it allows you to understand how the competitors, the swing in impact it has on the output, from 231,000 to 622,000, depending on how many competitors enter in 2017. So it's quite significant. One of the things you can do with these is you can actually grab any one of these bars and drag them out. And then you can study. This creates a scatter plot. Remember, with the number of competitors, we're talking about a discrete distribution. We only have 1 or 2 or 3 or 0 or -1 competitors entering the marketplace. In other words, they may drop out. And so we have these straight lines that define what's going on with the net present value based on the number of competitors that are entering the marketplace. And again, you can move these around to study how it affects the percentiles in each quadrant. Another interesting one to look at is this. Unlike the discrete distribution, this is a continuous distribution, and you can see with a 0.11 coefficient value, this is about as random as you can get. But one of the things you can do in here is you can go into the net present value line, type in 0.365 because that's our target. It moves the line down to that point, and you can say, for example, sales volume in 2016, if it's at 3,000 or let's say 2,400, there's a 12.7% chance that the sales volume will be 2,400 and you'll be earning less than 365,000. The opposite of that is there's a almost 43% chance that you'll be earning more than $365,000 and there'll be sales volume above 2,400 units. You can also take a look at the information tabularly. So this little button right here allows you to view all the statistics for every single output and every single input. So here are the basic statistics, and then values at each percentile by fifths. And if you like, you can change, you have the ability to add different numbers. For example, if you want to see the value at the first percentile, just type in 1, and it finds that value for you. Or at the 99th, for example, and it finds that value for you. Or you can type in a certain number, like that, and it gives you the percentile value at that stage. So just like the charts and graphs, you can grab this and report it in Excel. This looks like an Excel spreadsheet, but it's actually not. And in a moment, we'll actually have an Excel spreadsheet. So here's that report. For the detailed statistics. Looks like I flipped the, I flipped the table. So my 99th, my first percentile value and my 99th percentile values are actually horizontal rather than, I accidentally clicked on the flip button, but it's all available there. Sometimes people ask, where's the, oops, I just deleted everything. Hold on. Sorry about that. I clicked the X button a little bit too quick. For transparency's sake, the little X of I button shows you the values for every random number that was sampled for every single input and output. So in this case, I reduced the number of iterations down to 500, and here are the values for all 500 iterations. So this is the raw simulation data from which we can analyze, from which we generate all the charts and graphs and other reports. So that's available to you if you need to take a closer look at it. Another nice feature is a model window. So sometimes we need to report our model and our assumptions as well. When you click on the model window, it opens up a window that shows you the distributions that were used for each of the functions, or for each of the inputs. It also identifies where the outputs are and any correlations that were put together. And just like all the other ones, you can report this in Excel for reporting purposes. Okay. I apologize, I'm clicking things a little bit too quickly here. I X'd out of at-risk. We'll be back up in a second. Okay, there it is. All right. So now we've studied one of the projects. We can go ahead and apply all, the same types of principles to all the other projects, but that would take a long time. So what we're going to do now is we're going to focus on the model summary, and we're going to begin to explore which projects should we take on to maximize our net present value number while retaining the budget, the amount of finite resources we have to devote to this particular portfolio. We use RISKOptimizer to do that. So let's click on RISKOptimizer and model definition. So in the model definition window, what we're doing is we're going to be maximizing cell D24, which is right here. And we're going to be doing that around a mean. Sometimes we want to do the optimization around a standard deviation to avoid volatility. And so instead of using a maximum, you'd want to use a minimum for the standard deviation, typically anyway. Another thing that we're doing is we're going to adjust cells that we have control over. So the cells that we have control over are these, which is which project do we select. And so during the optimization process, at-risk is going to be selecting some number of these, running a simulation, then selecting another set, running another simulation, and comparing the results, and doing that over and over again until we come up with the optimal number or configuration of projects to have to retain it in our portfolio that will be within the budget. And the budget is defined here. It's our constraint. So we're going to try and hit that budget within 95%. So in other words, we're going to try to be about 5% lower than the budget. So that's the basics for setting up the optimization model. So the next step now is to start. Okay. You know what? I forgot to do something. Let me stop this for a moment. I'm going to change this to 1, and just to sort of speed things up because we're already running short on time. And change the iterations to 1, and then we're going to go back to the optimization. Okay, so what's happening here is these numbers are being changed, and as soon as we find a configuration that meets the constraints, we keep that and start comparing it. So what happened is we started at essentially this level. So we're at $1.2 million, and then we found another better solution. And every time we find another better solution, I'm going to pause this just for a second, the output graph is updated. Let's restart that. Okay. And so we're up to a little bit more than $1.8 million. So I'm going to reduce this now so you can see those numbers change. And the last time I ran this, it took about 2 minutes or so to achieve a sort of a plateau, like we couldn't find a better solution. It was at about $2 million. So let's go back up. So it's plateaued now at about 1.8, and in a few moments, you'll see it pop up to about $2 million. So what's happening now is we're taking each project and simulating all 8 of those projects while choosing some projects to keep or not. And then we're doing that again and comparing the results, and then choosing another configuration of projects and comparing those results. Here we popped up to a little over $2 million. Okay, so we're going to stop this optimization now. And we are not going to restore the original adjustable values. If you recall, these were all chosen, and we were way over our budget. And instead, we're going to use the configuration that Atrisk came up with, a RISKOptimizer. We're also going to take a look at an optimization summary. So here's our summary, our fancy little graph. Here's the goal of our optimization. Here's where we ended up for the best value found for cell, I think it was C or D24, which is $2,108,000. And this sort of tabularly explains what we did with the adjustable cell values. The original is 1, we kept that 1. The original is 1, but we discarded it. And you can see that as you go down through here. This is not so fun to look at. I prefer to look at the actual model, because this tells us which items, which projects were chosen to maximize our profit while staying below our budget. And that's the power of RISKOptimizer.